Welcome back, everyone. So we're going to continue working through these remaining examples for 4.3, the definite integral. So the first example here is just kind of showing you the different ways that we can write the definite integral given particular functions, especially in this case, functions with symmetry. So we'll just note that the area is going to equal the integral from -2 to 2 of x squared minus 4 dx. So that's going to be our area under the curve, which is going to have, in this case, a signed area. So it's going to be positive and negative numbers that'll be adding and subtracting from each other. But when we actually get to evaluating this type of integral, it's going to be useful to use symmetry and use maybe splitting up of pieces to make it a little bit easier. So a different way we could write this, noting that we have symmetry about the x-axis, right? So x squared minus 4 is an even function. Instead of going from -2 to 2, I could integrate from 0 to 2. And then double it. So multiply by 2 and simply evaluate that first integral. And the reason why we're going to want to do that is because at 0, it might be easier to evaluate once we have the fundamental theorem of calculus. So then different ways we could also approach it is to take the two positive areas and combine them together. So we could write this as 2 times the integral from 1 to 2, let's say. So that's going to be doubling that positive area and then adding that to the negative area. Excuse me. So we could do it that way and split it into two separate integrals. And there's a whole host of other ways you could approach it as well. So again, I would just try to find a couple different ways to write it that you think might be useful. All right, so getting to our additional exercises, we're going to use that idea of the definite integral for the first couple of questions here, and then on the bottom, we'll do another Riemann sum example. So for number 1, we've got a graph that has 2 quarter circles, which we can see on the left over here. One is below the axis, one is above the axis, so one is going to have positive area, one's going to have negative area. And then we've got a line segment. So we want to figure out the integral from -4 to 3 of f of x dx. So that's our goal. So the first thing we're going to want to do if we're given a graphical example is to close off our graph with the x-axis. So clearly these spaces below, we want to close them off to denote where our areas are going to be. And we can see here that we're going to have some positive areas and some negative areas. All right, so this is really then going to be equal to each separate area added together. So we could start with this negative quarter circle area there. So we can see the radius is 1 of our quarter circle. So we're going to get 1/4 times pi r squared, which in this case is just 1 squared. But it is below the axis, so we'll add a negative sign to that area. So we're going to get -pi/4 plus, and then the area of the second quarter circle is going to be radius 3. So we'll have 1/4 pi times 3 squared. And then for the two triangles, we could do the area of the triangle, so 1/2 base times height. But if you notice, right, these are the same triangles in terms of height and base, which means that because one is above and below, when we combine these, they're going to cancel each other out. It's going to equal 0. So again, using that symmetry of the graph, of a given graph, is going to be very useful in saving you time. So in this case, we don't even actually have to calculate the areas because we can see that the base and height of both of those right triangles are the same. So they will equal 0. So what we're going to end up with is -pi/4 plus 9pi/4, or 9/4 pi, which gives us 8pi/4, which is just 2 pi. So the integral from -4 to 3 of f of x dx is 2 pi in this case. For number 2, this is going to be a case where we're not going to use geometry specifically, but we're going to use what we know about the graph itself, or the shape of the graph. So we want to determine whether the inequality 2 less than or equal to the integral from -1 to 1 of the square root of 1 plus x squared dx is also less than or equal to 2 rad 2. So we want to create a boundary for an upper bound and a lower bound for what the area underneath that curve is. So in this case, we don't have a way of evaluating this. So note, even if we try the limit of the Riemann sum definition, we're going to have our f of x expression is going to be the square root of some stuff. And we don't have any summation formulas for square roots. So without some sort of formula to use here, that's going to create an issue. It's going to make it a little bit trickier to work out. So what we're going to want to do then is we're going to want to look at the graph and see if we can come up with an argument for these inequalities. So the first thing that I'll notice, which I'll put over on the left here, is we can simplify this inequality first. So we'll just note that the integral from -1 to 1 of rad 1 plus x squared dx is the same as 2 times the integral from 0 to 1 of rad 1 plus x squared dx. And that's again using from our previous example that we started the video off with, using symmetry. So we know that this function f of x is even, right? So it's symmetric about the y-axis. You can test it there by plugging in -x and seeing that you get the same exact output values. So we could simplify this a little bit, which would mean that our inequality would slightly change. So the inequality actually then that we're going to prove, if we substitute in the second integral, is going to allow us to cancel a 2 out of everything. So really what we want to show is that 1 is less than or equal to the integral from 0 to 1, rad 1 plus x squared dx, which is less than 1 radical 2. So it's going to create a little bit easier way to prove it. You don't have to do it this way, but it is the way that I will end up looking at it. All right, so let's look at the graph of the square root of 1 plus x squared. So we want to go from 0 to 1. So at 0, our graph is going to be at 1. And at 1, our graph is going to be at the square root of 2. So our 2 points on our graph, which we will use as reference, is going to be 0, 1, and 1 comma radical 2. So we'll just note this is 1 rad 2. And that point is just 0, 1. And then we know it's a square root function. If we take the derivative of this square root function, we'll see that we still get positive numbers on this domain. So it's an increasing function. So it's going to have some increasing behavior, right? So maybe it looks sort of like a square root function. The concavity might be slightly off here, but that's okay. We won't need it for the actual proof here. So then we're finding the area underneath this red curve. So we want to show that it's stuck between 1 and the square root of 2, and now we can actually use a little bit of geometry. So we'll note that if I just drew a straight line from the initial point of the curve at 0, which is 0, 1, I get a rectangle with area 1. And if I, let's see here, we can use a different color, maybe orange. If I drew a line from radical 2 and created a rectangle, that area would be radical 2 by 1, so radical 2. So this is more of a proof by picture sort of problem. And so we can see here clearly that the curve's area, which is going to be above, right? We're going to have this extra portion here is going to be above 1, but it's going to be smaller than our rectangle with height radical 2. Okay, so we'll say by our picture, the integral from 0 to 1 of rad 1 plus x squared dx is going to be between those two values. So this is going to be a rare example where a proof by picture is really going to be feasible. but we can clearly see there that we're going to have that result be true. All right, so then for number 3, we're just going to use that definite integral notation with some numbers to kind of rewrite. And for each of these, it might be useful to actually maybe draw a picture as well. So we'll just note for our middle integral there, the integral from 1 to negative 2 h of x dx equals 8, the limits of integration are flipped, right? So it's from greatest to least as opposed to what it's normally going to look like, which is least to greatest, left to right. So we probably want to rewrite this by flipping those limits of integration, which if you remember from our properties, if we reverse the limits of integration, we take the opposite sign of the area. So the integral from negative 2 to 1 of h of x dx is going to be negative 8. All right. So we want to figure out the integral for a from negative 1 to 0 of h of x dx. So let's kind of draw our picture here. So pretty much we've got information between negative 2 and 1. So we want to figure out the area from negative 1 to 0. Let's look at what we know about the area from negative 1 to 1. We know that that is 0. So but we don't know which side is positive, which side is negative. But if we look over here, we can see that 0 to 1 is 5. So from 0 to 1, the area here is 5, which means if the integral from negative 1 to 1 of h of x is equal to 0, we know that this area is going to have to be negative. Right? Now, they might be symmetric. They might not be. We don't know. We don't know if our curve passes through the origin. So in order for negative 1 to 1 to equal 0, which is what we know, that means that this would have to equal negative 5. So you can kind of do this pictorially. The way we could do it kind of just using the notation is take the integral from negative 1 to 1 and subtract the integral from 0 to 1. So what that's going to do then is if I subtract this, then we lose that area from 0 to 1, and we're left with just negative 1 to 0. So we would end up with 0 minus 5, which of course is the same thing we got by picture. So I don't really mind which way you do it, but just try to find a way that's going to work best for you, either pictorially or using the notation. All right, so for b, we've got the integral from negative 2 to negative 1. So the integral, let's use smaller font here, negative 2 to negative 1, h of x dx. So that's going to be the integral from negative 2 to 1 h of x dx, that middle integral. And what we're going to want to do is subtract off everything from negative 1 to 1, which we also know. And again, you could do this by picture if you wanted to. So that's going to give us our answer, which is going to be negative 8 minus, and then the integral is just 0. So that's just negative 8. Excellent. So what that tells us then is that this area is going to be negative 8. Oops. And then, let's see here. So we've got, this is going to be the constant multiple. So we can just rewrite this as 3 times the integral from negative 2 to 1 h of x dx, which is just going to be 3 times negative 8, which is negative 24. And so this is just a case of using that notation. Again, drawing a picture can help, so definitely use that to your advantage. So for our last example then, we're going to do another Riemann sum example with the limit of the Riemann sum. So what we'll notice here is what we need. We need delta x, and we need to know f of x sub I. So we want those two things. So delta x then is going to be 2 minus 1 over n, which is just 1 over n. And then x sub I again is a plus delta x times I, which is going to be 1 plus delta x is 1 over n times I, so that's just going to be 1 plus I over n. So then f of x sub I is going to be x sub I squared, right? Our function is just x squared, so it'll be 1 plus I over n squared, which we can note, we can just expand this ahead of time. So 1 plus 2I over n plus I squared over n squared. All right. So our definite integral then is going to equal the limit as n goes to infinity of the sum of I equals 1 to n of f of x sub I, which is our expanded expression there, times delta x times 1 over n. And now you can, again, decide on how you want to expand things, work it out. This is going to be exactly similar to what we did in 4.2. So let's see here. I'm going to split each sum after multiplying my 1 over n into each term. So 1 times 1 over n is just 1 over n, so I'm going to get 1 over n times the sum of I equals 1, to n of 1, plus 2I over n is going to be 2I over n squared, so we can factor out a 2 over n squared, and we'll have the sum of I equals 1 to n of just I. And then finally we'll have I squared over n cubed, so we can factor out n cubed, and we'll have the sum of I equals 1 to n of I squared. And now we can just evaluate. So let's see what we get here. So we're going to get, let's just make a quick note here. This is equal to n. So those will just cancel and become 1. So we'll get the limit as n goes to infinity of 1 plus, and then we'll have 2 over n squared times n plus 1 over 2 plus 1 over n cubed times n plus 1 times 2n plus 1 over 6. Again, just using those series formulas, put that all in parentheses. And now from this step, you can just evaluate. If you want to, distribute everything out just to see, you can. So we'll just note there's going to be a 2n squared in the numerator and a 2n squared in the denominator. So that's just going to equal 1. The limit of 1 is just 1. So we'll have 1 plus 1 as our first two terms plus. And then for our last expression, we're going to have a 2n cubed and a 6n cubed as the lead coefficients. So we'll get 2 6 or 1/3. So our answer is going to be 2 1/3 or 7/3. And we're done. And what I'll just note here is, again, where we're going to head in 4.4. So the way we're going to interpret this once we've looked at the fundamental theorem of calculus is that the integral from 1 to 2 of x squared dx, instead of doing this limit of a Riemann sum process, which can be extremely messy, especially if our functions become more complicated, becomes much simpler with the fundamental theorem of calculus. So what the fundamental theorem of calculus tells us, part 2 at least, or part 1, depending on which textbook you're looking at, is that I can evaluate this integral, definite integral, using antiderivatives. So this is the way it would work. I take the antiderivative of x squared, which is going to be 1/3 x cubed, and then I'm going to evaluate it at 2 and 1 and subtract the top value minus the bottom value. So that's going to be 1/3 times 2 cubed minus 1/3 times 1 cubed, which is going to give me 8/3 minus 1/3, which is, as we calculated above, 7/3, right? So this will always be true. And what you'll notice is the fundamental theorem of calculus is like our product rule, quotient rule, chain rule. It's a simplification of the integration process that is just much easier to deal with computationally than this limit of a Riemann sum process. We need to know both because this is the foundation, but that foundation then can be simplified to this algebraic method. So that's going to conclude our notes for 4.3. Definitely drop by the office hours if you have questions or shoot me an email. And until I see you next time, take care.